Hi, this is Purnima Mahalingam, and you're watching video lecture series on solar and wind energy systems. In this video, today we are going to discuss about solar refrigerations, which is sustainable cooling solutions. Come, let's go into the video. Here, first we can see the empathy part. Um, Here, what happened is solar refrigerations, which is harness solar thermal energy for cooling global cooling demand, will trip by 2050. We know that this technology reduces really on electricity intensive vapor compensation systems. It is critical for off-grid cold chains in developing regions. We have seen the solar generator, condenser, and absorbers and evaporators and solar refrigerations, etc., which is the cooling systems where the heat energy is converted into the cooling energy. Here comes that one. So in 2025, there is a demand of cooling demand systems. So this is our empathy part. Now coming to and the next part of a solar thermal system, the heat sources, where the heat sources is we have flat plate collectors and evaporated tube collectors and concentrated collectors. We have three sources where about 100 degrees Celsius for domestic hot water, 200 degrees Celsius for absorption chillness, and over 200 degrees Celsius for industrial scales. Here, the solar thermal collectors converts the sunlight into heat and the heat transfer to your working fluid for the chilling cycles. The next one is absorption refrigerations weakened with the core technology. What about they're using absorption technology? Here we can see the heat powered cooling. This technology convert heat directly into the cooling power. This relies on absorption and refrigeration path. Okay, here what type of water is lithium bromine water for AC and ammonium water for sub-zero temperatures. Okay, here we can see the heat energy. We have seen that the vapors and we have a cooling process. The absorbed chillness have minimal moving part, lower nozzle, and low noise, long lifespan, and single effects. Chilling typically achieves concentrated powers of 0.6 to 0.8. Okay. Now coming to the system in integrations, how it is work. So solar heat input. So input is a solar heat. We have a refrigeration vaporization process and cooling effect and reabsorptions and repeats. So these seamlessly integrated ensures continuous cooling even during period without direct sunlight happens. Thermal storage tanks typically 500 to 2000 liters, which allows for nighttime operations. So this sometimes maybe 24 into 7 operations also. This here we have an advantages and environmental impact comes here within 70 percentage of electricity says obviously that is a main advantage. It's a main goal too, that significant reduction in power consumptions and 1 ton of carbon dioxide CO2 reduction. CO2 emission is reduced about 1 ton up to 1 ton of CO2 emissions reductions for annually, and zero ozone depletions. The main process zero ozone depletions and was eliminated half harmless refrigerations. So solar refrigeration offers low price, low operating cost due to free cost. Solar fuels, it provides enhancing energy which is independent, especially in the remote areas. Now coming to the key applications, case studies. We have so many case studies here. Here the solar refrigeration system supports commercial cooling. Here we can see the commercial cooling, food preservatives. We can see the food preservatives and vaccine storages. We have so many, we can see the so many commercial food preservative vaccines and provide off-grid ice making and data centers. These applications are vital in developing regions and the remote areas. Very useful in this. Here comes the challenges, and what are the challenges and solutions we are facing is solar refrigerations. We have an high capital cost and large footprints and the solar intermitting and maintenance expertise. These are the main challenges, and we have a solutions. The main specialized skills are needed for absorption chillers, standardization on moistures, which is with the help of system system. And solar intermittency, they reduce thermal storages or hybrid systems for continuous operations. And what happens, the large footprint requires significant spaces for collectors and storages, and which the hybrid designs can reduce this. Okay. Now, coming to the futures of solar refrigerations, immense potential, we can say, on reshape global cooling. It will integrate with the smart grid technology and AI for optimization. Here comes the optimizations also. It can be included. This technology is crucial for advanced and ideate part of design thinking process. The technology is critical for achieving goals, global climate goals. It also enhances the energy storage targets, which it widespread adoptions with benefits of commercial, industrials, and agriculture structures. So these are the future scope. And finally, we are coming with summarized part, and we have a summarizing of solar refrigeration systems. We have core technologies where heat powered cooling, refrigeration paths and characteristics, and we have solar the heat sources and system integrated. How it is work? In that we have seen solar input, heat input, vaporization, cooling effect, ray absorption, and repetitions, and uh, continuous cooling mechanisms. Okay. Now, challenge and solutions. We have, what are the challenges? High capital cost, large footprint, and a large solar intermittency and maintenance. It needs an expertise for maintaining the whole hardware structures. And finally, coming with an applications and future potentials. I hope you understood the topic. We will meet in next video. Thank you so much for watching. Have a nice day.